Welcome to this presentation on Essentials of LC Troubleshooting, where the subtitle is Some Problems Just Never Go Away. So here's an outline of the presentation. First, for a little bit of context, I'll talk a little bit about the LCGC LC Troubleshooting wall chart, and then take a little side note and talk about what AI knows about LC troubleshooting today. And then we'll get into the real content. So first talking about some of the best practices for effective troubleshooting, and then talking about some specific problems related to pressure, some specific problems related to peak shape and width, and some specific problems related to baselines, and then we'll wrap things up. So first I just want to point out that a lot of the material for the presentation today is drawn from a series of articles I've written recently for the LC Troubleshooting column for LCGC Magazine. So if you're unfamiliar with the column, you can go to chromatographyonline.com, go to the columns drop down and choose the LC Troubleshooting column, and there you will see articles listed like the one shown here. Now, one of the resources that LCGC offers for LC troubleshooting is the so-called wall chart. This is a snapshot of an electronic version of the wall chart, so you can literally get a paper copy to hang on your wall, but there's also an electronic version that has the tabs shown here with different topics related to sensitivity recovery, baselines, and so on. And earlier, I guess a couple of years ago, in thinking about some new or some new articles to write for LC troubleshooting, I was thinking that there are just some topics in LC troubleshooting that are really timeless, that no matter how much the instrumentation improves over time, and it certainly has improved tremendously over the past decades, that we still have some problems that keep coming up over and over again. And a lot of these problems are reflected in the wall chart. And so a summary of that series of articles that I started a little over 2 years ago is shown here. So starting with Troubleshooting 101, essential principles of effective troubleshooting, and then getting into the more topical aspects. So you see there are 6 parts, including a continuation of the second part. And today in this presentation, I'm going to be focusing on the content contained in 4 of those articles, which are highlighted here. So again, basic principles of troubleshooting, pressure problems, peak shape problems, and baseline problems. But before we get into that, I think it's kind of interesting to think about what artificial intelligence has to offer these days in the way of troubleshooting. And so I've been playing around with ChatGPT a little bit, just like a lot of people have. And recently I asked ChatGPT, what should I do if the pressure on my HPLC instrument is too high? And this is what it came back with. It came back with a series of ideas here, and I've kind of put my rating next to each one of them. So the first 3 are quite reasonable. It says things like check for any clogs or debris in the column that may be causing the pressure pressure to increase. This is certainly very reasonable. Second one is check to make sure that the mole phase is properly prepared and filtered. This is also reasonable. Third one is check to see if the flow rate is too high. This can lead to increased pressure, and certainly that is the case. If we forget to use the proper flow rate, then we could experience a pressure that is higher than we expect. But then after that, things get a little bit questionable. It talks about the injection volume affecting the pressure, which doesn't really make sense. It even goes on to talk about how leaks can cause increased pressure, which doesn't make any physical sense at all. And I think the last one is particularly interesting. It says if the detector is not calibrated correctly, it can cause increased pressure. I have no idea how this would be possible. But it does finish on a strong note saying that if you've checked all of these possibilities, it may be necessary to contact the manufacturer or a service technician for further assistance. Certainly, this is good advice. So I think the conclusion here from this little experiment is that we cannot fully rely on AI for troubleshooting, at least not yet. So if we then get into our content here, thinking about best practices for effective troubleshooting, I have 7 things that I want to talk about. And the first thing is that everything, I think we have to have this mindset that everything is possible. So I say this a lot in my own laboratory to my students and other people I work with. I think we really have to have an open mind and try to avoid overlooking possible explanations, even if they seem improbable. Certainly, some causes are more likely than others, but we have to have an open mind so that we don't overlook something that we could come to regret later. Second point is to change one thing at a time. So if, for example, we have a problem with the flow rate from a pump, we could come up with the idea that one, either the inlet or outlet check valve is experiencing a problem, and if we just change both the check valves at the same time, then we're likely to solve the problem. The problem is with that approach that even if we we do find that replacing both check valves does solve the problem, in the end we don't know which of the check valves is actually producing the problem. So this is a waste of resources, and also we run the risk of losing information because we don't know what the real problem was, which we may regret not having that information later. So even though it feels maybe inefficient at times to work very methodically through a problem, I think it's generally speaking wise to just change one thing at a time so that we have a clear way to interpret the results of our changes. Third point here is to do no harm. So it's quite common to borrow instrument parts from a working instrument in the lab, and we have to be disciplined and make sure that after we've used that part from a working instrument as part of our troubleshooting process, that we put the part back. Otherwise, we can really end up with a confusing mess, not knowing or understanding what parts originated from which instruments and where they are in the lab. So good idea to return parts to their parent instruments after we've borrowed them for a troubleshooting exercise. Fourth point is that drawers are not repair centers. So I think this is a bad habit that a lot of people have. I'll admit to doing this myself in the past. And we really should avoid the temptation to put parts back in drawers, especially if they're known to be bad or questionable. If they're known to be bad, just throw them away because they're not going to repair themselves sitting in the drawer. And if they're questionable, if we don't know if the part is good or bad, it's best to determine the functionality or the state of the part before we put it in the drawer. And if we find out that it is in fact a faulty part, then get rid of it. If we find out that the part is functional, then it shouldn't go in the drawer, it should stay in the instrument. And a lot of times I think there's a rush to get the instrument back online, and we have the idea that we'll come back and evaluate the state of the part later, but usually that later never really happens. The fifth point here is that it's really important to have a good idea about what are your expectations for how the instrument should work. The first step very often to an effective troubleshooting exercise is to recognize that there's a problem to be solved in the first place. And later on, as we get into other topics here, I'll talk a little bit about how we manage our expectations. But developing the know-how and the understanding to have those expectations is very important. Sixth point is that documentation really helps in the long run. And again, I think in the rush to get an instrument back online, it's tempting to sort of skip over the part of the troubleshooting process where we write down the changes we made and how different changes affected instrument performance. But we really need to be disciplined and document what we're doing right away, because if we don't write it down, then we lose that valuable information about what happened, which could be valuable in troubleshooting exercises later on in the future. Finally, know when to ask for help. So some problems are really best solved by the experts. As users, we don't know everything about the instrument. And if we feel like we've tried all the reasonable steps to troubleshooting a problem, then it's okay to call in an expert, representative of the manufacturer or of some other service vendor, and hand the problem off to them. Now, getting into some specific problems. The first category here is pressure problems, and I've divided these problems into situations where the pressure we see is too high, pressure we see is too low, or the pressure we see is highly variable. And so this is the first place where we can talk about expectations. The only way we can know if the pressure we're seeing is too high or too low is to have an expectation about what we should see, something to compare our observation against. So for open tubes, like capillaries that connect different parts of the instrument, we have the equation shown here that relates the pressure drop across a piece of tubing to the critical variables like the viscosity of the mobile phase, the length of the tubing, the flow rate through the tubing, and the diameter of the tubing. If we're dealing with a column that has particles in it, then we have a different expression, where here we have the pressure drop across the column related also to the viscosity of the mobile phase, the velocity of the mobile phase, the length of the column, and the size of the particles inside the column, and a flow resistance factor here, which is more or less a constant for most situations. Now, once we understand these equations and the terms in them, of course, we could sit down with a calculator and make calculations for specific situations, or perhaps build a tool and a spreadsheet. But I just want to make you aware that tools already exist for this, freely available tools that run in a web browser. And the two that I'm showing you here are developed and maintained by my research group. So the first one here, if you go to multidlc.org/dispersion calculator, most of this tool is made for estimating contributions to dispersion in HPLC systems. But one of the things we also do is calculate the pressure drop across different parts of the system. And so these are all different pieces of tubing. For example, tubing before the column, tubing after the column, and so on. This is a very handy way to easily calculate the pressure drop so you know what to expect based on inputs up here in this section that correspond to the variables in the equation. Now for the column itself, we have a different tool. This is our HPLC simulator. Again, if you go to the same website, but /HPLC sim, here you can put in all of the typical variables we would think about in an LC experiment, the temperature, the flow rate, the column dimensions, the particle size, and so on. And here this calculator calculates for you the pressure drop across the column that we should expect for the conditions that we have entered. So again, this is a really easy and simple, easily accessible way for you to have good expectations about the kinds of pressures you should see in your system. So once we have developed our expectations and we have something to compare to, then again, we have cases where the pressure is lower than we expect or higher than we expect, or sometimes we see that the pressure is fluctuating a lot. So in the case of a pressure that's too low, One of the things that can happen is a partial blockage of the inlet filter to the solvent line in our solvent bottle. And if this happens, basically the pump becomes starved for a mobile phase and it won't be able to deliver the flow rate we expect through the column, and therefore the pressure we will see will be lower than we expect. Of course, if there's a leak somewhere downstream from the pump where the pressure is measured, then that can also result in a pressure that is lower than we expect. Usually, cases where we see pressure that's highly variable or fluctuating somehow have to do with something that's going wrong in the pump. So if we have one or both check valves that are sticking so that the ball in the check valve is not releasing properly, this can lead to highly variable pressure. One problem we see a lot is air bubbles that get stuck in the pump head can also lead to highly variable pressure. If we have pressures that are higher than expected, this usually is related to some partial blockage of the flow somewhere in the system. So this picture shows a situation where the inlet frit to the column itself is partially occluded, which is going to restrict the flow through the column and lead to a higher than expected pressure. Similarly, we can have a situation where, for example, a inline filter filtering the mobile phase between the injector and the column, for example, might be partially occluded, and we can just replace the filter to return the pressure back to normal. Now, moving on to peak shape, there are many ways that things can go wrong with peak shape, and those shapes are summarized here. So we're going to talk through all 8 situations here really briefly. Go to the first case. This is the perfect peak. So in the absolute best case, we should see peaks that are highly symmetrical and shapes that are described by a Gaussian distribution. Sometimes we get close to this kind of perfect shape, but I would say rarely this is exactly observed in practice. Usually peaks are slightly misshapen, and that's quite normal. Now, if we go to the situation where we see no peak, there are many reasons that this can happen, but some of the common ones are very simple things like the vial is empty, sample vial is empty, or the volume in the vial is too low for the needle to actually reach the liquid. If we choose conditions where the retention is too high so that we don't see an analyte eluted during the analysis time, obviously we won't see a peak. Or if the concentration of the analyte is too low or the detector response is not strong enough, then we won't see any peak. So solutions to these, you can imagine simple things like making sure we have enough volume in the vial, adjusting the elution conditions to make sure that the peaks actually, or the analytes actually elute from the column, or increasing the analyte concentration so we give ourselves a good chance of actually seeing a peak at the detector. Moving on to broad peaks, usually these are related to the column not performing as expected. So this could be just due to normal, let's say, wear and tear on the column where the peak width slowly increases over time, or maybe there's a more serious problem like a partially occluded frit, which is causing uneven flow through the column. Broad peaks can also be caused by greater than expected dispersion or broadening of peaks in the system, but outside of the column. So for example, connecting capillaries that are too long or too wide, injection volumes that are too large, and things like this. So in a situation like this, we can try replacing the column to see if the column itself is the problem. And if we suspect that the problem is in the rest of the LC system, then we have to work through systematically and try to find the part of the system that's actually causing the peak broadening. Tailing peaks, again, lots of possible reasons for tailing peaks, but some of the more common ones are listed here. So if we have very strong interactions between the analyte and the column material, or uh, instrument components in the flow path that the analyte sees. This can lead to tail and peaks. Sometimes, if there's a bad connection, a bad fluidic connection, like a capillary that's not properly seated, this can act like a small mixing chamber and lead to a tail and peak like the one shown here. Or if a column is failing very badly, one of the symptoms of a failing column can be a badly tailing peak as well. Fronting peaks. So this is, I would say, less common in LC than tailing peaks. However, under some conditions, injecting too much of an analyte, too much analyte mass, can lead to an asymmetric peak like the one shown here, where more of the mass of the peak or the peak area appears on the front side of the peak rather than on the back side. Moving on to split peaks like the one shown here. So this kind of peak shape could be due to two compounds eluting close together that aren't resolved, but we can also see this kind of peak shape for a single analyte, and this obviously is not ideal at all. And I would say usually this is related to column failure. So a couple of possible ways that the column can fail to lead to this kind of result are that we can have a reorganization of particles inside the column that leads to uneven flow paths or very different flow velocities across the radius of the column. We can also have, like was shown a few slides ago, a partially occluded frit, especially on the inlet side, can lead to uneven flow across the radius of the column, and this can lead to a split peak shape like this as well. So in a case like this, replacing the column even temporarily to see if all columns in a system produce this kind of peak shape, or if this peak shape is unique to a particular column, can help us diagnose whether a split peak like this that we see is related to the column itself. The next one here is what I call fuzzy peak. So we see a smooth signal for most of the peak, but then at the top we have this very sort of shaggy or fuzzy appearance. And I would say most of the time this is due to the fact that the signal is so high that we say that the detector is saturated. In other words, the signal can't go any higher. And usually in a case like this, the fuzzy part of the signal on the top is just noise. The detector is not really responding to changes in concentration of the analyte anymore. And so a very easy way to find out if this is actually the cause is to simply inject less analyte and see if we get a more normal peak shape. Finally, we have here what we call a negative peak. So in this particular case, the peak shape is quite nice in the sense that it's narrow and symmetrical, but it's inverted relative to what we normally expect. So at least in the case of UV detection, the two most common causes of this are cases where the analyte eluting from the column is producing a smaller detector response than the mobile phase itself. So if the mobile phase absorbs quite a bit of light, but the analyte eluting actually is more transparent than the mobile phase or absorbs less, then we can have a negative peak like this. Or in the case of UV detection where we use a reference wavelength to adjust the UV detector signal, and the analyte absorbs more strongly at the reference wavelength than at the primary detection wavelength, we can also end up with a negative peak like this. Now, getting into the last topic here, baseline problems. Here we have a situation where we have solvent impurities in the solvents that are used in the mobile phase, which lead to baselines that are not desirable. So on the left here, this is a case where we're using UV detection, and the red trace here shows a pretty flat baseline. The peak here at about 3 minutes is the compound we're interested in. And we compare that chromatogram to the chromatogram in black, where we see that the peak of interest looks similar, but we have this huge peak at the end. This is occurring at the end of our solvent gradient. And so comparison of the chromatograms obtained using solvents from these two suppliers shows us that this huge peak at the end is coming from some impurity in the solvent from supplier A. We can also observe things like this with mass spec detection. Here in this comparison, we have the total ion chromatogram, and we see again in the case of the red chromatogram that we have a really dramatic increase in the signal toward the end of the analysis. In this case, we're doing gradient elution again, so there's something in the B solvent, the organic solvent, that is really producing a lot of ions in the mass spec. And by comparing the signals we get from uh, we get in the two chromatograms when we use solvents from the two different suppliers is a really effective way of isolating the problem to the solvent itself. The last example here, we have a situation on the left that is highly undesirable. This is a gradient elution analysis where we see it that initially the baseline is pretty stable, but then as we get into the gradient, it really slopes off dramatically. And this is because we're using a detector wavelength here in the UV that's too short. It's one of the mobile phase components is absorbing very strongly there. And when we decrease the amount of that solvent in the mobile phase, the apparent absorbance goes down dramatically. Whereas if we change to a more appropriate wavelength, 254 nanometers, where the solvent doesn't absorb so strongly, we end up with a relatively much flatter baseline. So we can have some really strange baseline shapes that occur just due to using detector settings that are really not very appropriate. So we've really only scratched the surface here in terms of all the ways that things can go wrong in a system, but we've touched on some of the really persistent problems that we see with pressure and peak shapes and baselines that really tend to not go away. So to summarize here, the first step in effective troubleshooting is recognize that there's a problem, that something doesn't look right, and the ability to recognize that there is a problem really depends on our knowledge base, how much information we carry around in our heads about what we expect to see, so that when we see something that looks different, we can actually recognize that there's a problem. And once we start a troubleshooting exercise, being disciplined and following a systematic approach will save time, energy, and resources in the long run.